So yeah, at the start, I'll just give an intro to JWST coronagraphy and make sure everyone's got a rough, similar foundation to what we'll be talking about. And then after that, I'm really going to spend the bulk of the talk talking about how to reduce and analyze JWST data with spaceKLIP. And I'll be swapping back and forth between a sort of live tutorial demonstration. I might not do everything live. I have some like files I'll show you. Okay, so before we kick off properly, I have a few quick caveats. Firstly, the calibration observations are still ongoing. So what that means is some of the steps I'm going to show you, and I'll try and point these out when they happen, are really us trying to sidestep the fact that our calibration files aren't perfect. And in the future, maybe you wouldn't want to do those steps, or you might want to tackle things slightly differently. So just keep that in mind. And on a similar vein, we've only really had access to this data for 3 months. I know the commissioning teams have had it a little longer, but as you might imagine, that has pushed us in certain ways in terms of just what we could do in the time available. And certainly, I wouldn't say what I'm going to present to you today is the perfect only way you should be analyzing this sort of data. And different approaches are definitely welcomed and encouraged. Okay, so let's kick things off with just giving you a bit of an introduction. So for those who aren't aware, JWST has a ton of modes on our board across 4 different instruments that do different things for different science cases. And we're really honing into today on one particular mode called Coronagraphy across these 2 instruments, NIRCam and MIRI. These span the full wavelength range of JWST or most of it, and they only work with imaging. So you can't do spectroscopy with coronagraphy with JWST, but you can do it from other instruments from the ground. So what does that mean? Well, you have a ton of filters that you can sort of exploit for coronagraphy, and this is the picture. This is all of them. So you have a few in the short wavelength channel of NIRCam on the left of this gray line, a ton in the long wavelength channel, and then you have a few filters with MIRI here in these sort of mid-infrared wavelengths. I would say probably these 3 here are really the workhorse coronagraphic filters for MIRI, because this 23 micron one, even though it probes this quite unique wavelength range, it has a very, very large inner working angle that sort of prohibits any sort of very high contrast imaging and sort of very, very short separations. So what might you want to use coronagraphy for? Well, in my case, for my science, I use it to look for planets. So here's a sort of GIF, as you can sort of imagine what coronagraphy does. On the left here, we have some astrophysical scene, and this black blob is the coronagraph. And you can see as you move that coronagraph in front of the star, it blocks the light from the star and diminishes quite significantly the flux we receive from it. And then as a sort of added step to coronagraphy that most people do is we perform some sort of PSF subtraction. So that coronagraphy can't get us all the way. So what we do is we try and model that residual stellar flux, or we try and understand its shape and its profile, and we can subtract that away. And if you can do that to a sufficient precision, then you can start to uncover objects very, very close to their host stars, like these planets you can see in the image on the right. So for JWST, we have a few different coronagraphs. There's these sort of standard coronagraphs, as I call them, that NIRCam has, and this one MIRI one at this 23 micron filter. And these are sort of, physical obscuring elements that physically block the light from the star. And then for MIRI, we have this sort of different technology, which is this 4-quadrant phase mask. The best way to imagine this is, you have these 4 different quadrants, and 2 of those quadrants are physically sort of offset from the others to produce this sort of pi phase offset between them. So what that means is if you can precisely position a star at the center, you get a sort of nulling effect, and the light from the star interferes destructively, and you can really reduce a lot of that stellar flux. So I won't go into these 2 in much more detail, but they have different cases for different, science applications. You can imagine this round mask has an advantage in that you have a full 360-degree coverage. And then the bar mask, while it doesn't have that, might let you push to smaller inner working angles for the JWST modes. Okay, and then that final step that I showed on that previous slide, that PSF subtraction, JWST has a few different techniques for this. So you can imagine you would observe some target, you think there's a planet around it, or there's a planet around it. There's some solar illumination hitting the telescope on the sun shield. How do we start to subtract away that stellar light? Well, There's two real techniques I think you can exploit for JWST. The first one is angular differential imaging. This is where you physically roll the telescope some amount of degrees, and then what happens is the planet should move in your field of view, but the star, while it's centered, all that structure, that residual stellar light, its shape shouldn't really change. It should stay pretty static. So if you start to subtract those images, you can see the planets between them. The only limit really for JWST with this technique is this solar illumination. We have to be really careful with the angles we point the telescope towards the sun to make sure it doesn't overheat. So really, we can only do this over sort of a 10 to 14 degree range, an absolute maximum. From the ground, we usually do this over a much, much broader range, and this subtraction technique is much, much more successful. And then the final technique I think we use for JWST is this reference differential imaging. And this is the idea that you sort of forget about that original target star. You point somewhere else in the sky and you find a star that, you know, has broadly similar properties to your target, you know, maybe same spectral type. It could be a lot brighter. That might help a little bit just in terms of reducing your exposure time. And then you try and get a picture of that residual stellar light from that star instead. And also for these observations, what you might see is that JWST will do like a small dither operation. It might like just make small, tiny movements around the star to get a sort of small library of realizations of these different residual stellar lights so that we can kind of find the best ones to subtract from our target observation.